involved drawing all of those forces acting on the object. Yesterday we drew a few free body diagrams. Drew a picture of a guy in an elevator as he accelerated upward. We saw that the normal force was bigger than the force of gravity. We drew a picture of a car that experienced an applied force by a tow truck, but maybe there was a force of friction acting backwards and a force of air resistance acting backwards. We also saw that there was a normal force and a force of gravity that balanced each other. Okay, we know how to draw these free body diagrams, but what do we do with them? What purpose do they serve when we're actually going to solve problems? Well, we learned yesterday that going to solve these problems, we look at our free body diagram and then say F net, the unbalanced force F net, is equal to the sum of the forces. So in this case, over here, it would be Fn plus Fg. In the second case, right here, the net force would be equal to what? The force of friction, the force of air resistance, and the force of the tow truck that we have right here. In any case, regardless of what the free body diagram looks like, F net will be equal to the sum of the forces, right, Cody? Now, sometimes we need to go that next step and say F net is also equal to M times A. So in that case, we'd sub in MA for F net. Sometimes we don't. Sometimes we can skip this step that's in red right here, depending upon what it is that we're looking for. Looking for acceleration, sub in MA. If you're not, then don't bother. Now it comes down to plugging in your numbers and solve for whatever it is that you're solving for. We don't have to really think too much at this point. Okay, the thinking's done. Now it's just a matter of plugging in numbers and solving for something. The one thing that we do have to be cautious of is our signs, positive and negative. If a force is to the left or downwards, we make it a negative value. If it's to the right or upwards, we make it a positive value. All right, I left you with a homework question last night on page 150 of your textbook. And it was kind of a tricky one, actually. How many people feel like they got that question? How many people did get the question? The answer's at the bottom, so you know if you got it or not. Yeah, good, actually, that's pretty good. It says, in the men's 4-man bobsled event at the Winter Olympics, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman is 630 newtons. So we got a mass here, right? The mass of the sled and the pilot and the brakeman and then 2 riders. During practice run, riders A and B exert average forces of 1220 and 1200 newtons forward, respectively, to accelerate the bobsled of mass 255, a pilot, and a brakeman. Then they jump in for the challenging ride down the 1.3 kilometer course. There's a force of friction acting at 430 newtons as the guys push the bobsled. We want to know what the average acceleration is. This question, the physics of this question is not all that hard. It's the wording of this question. It's almost a reading comp question as opposed to it's as much reading comp almost as it is physics, right? What do we have going on here? We got a mass of 630, we got a mass of 255, a mass of 98, a mass of 97. Like, what do we use here? Understand here, guys, that the 630 kilogram mass given to us is given to us to throw us off. It's given to us to see if we understand that we don't need it, that it's not relevant to the question. It doesn't say once that the mass of the guys in this sled and this sled is 630. It says, this is what it could be. This is what's allowed. Let me give you another scenario, okay? What if I had said, in the men's 4-man bobsled event in the Winter Olympics, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman is 630 kilograms, and you're allowed to paint your sled red? What if I said you're allowed to paint your sled red? Would that be relevant to the question? No, you're allowed to make the sled 630 kilograms. It doesn't mean you do any more than you're painting your sled red. You might, because you're allowed to, but it doesn't mean that that's what it is in this case. Does that make sense? we're not going to use that 630 because it doesn't say that that's what's actually being used in this question. It says that's what we're allowed to do, just like we're allowed to paint our sled pink or purple. Doesn't mean we do. What do we got here then? Here's my sled. The sled has a mass of 255 kilograms, but there's also two guys inside it with a mass of 98 and 97. Wait a sec, then my mass isn't 255. My mass is 97, 98, and 255. That gives me a total mass of 450, is that right? Now, what about the other two guys? This is only the mass of two of them, right? What about the mass of the two guys pushing? We don't know what that is. Does it matter? If I was analyzing this problem right here, where the tow truck is pulling this car, we don't care what the mass of the tow truck is, right? It's not being pulled. It's the thing doing the pulling. We don't care what the mass of the tow truck is. In fact, we don't even care really what does the pulling. It's just pulled with a certain force. If that's the case with the tow truck problem, then we don't care what the mass of the guy doing the pushing is. Who cares? It doesn't even matter whether it's two guys pushing or one guy pushing or 20 little kids pushing. The force that they push with is what matters. We've got two forces forward on this sled. One of them is a force of 1,200 newtons. The other one, we'll call it FA, is a force of 1,220 newtons. Now, as these guys are pushing it, there's also a force of friction backwards. It's going to be quite a bit smaller than these, 430 newtons. So far, so good? This question is now straightforward, right? We've sifted through what's important and what's not important. We've nailed the reading comp part of this. And now it's just a matter of doing the physics. Now we can say, oh, by the way, there are two more forces. I missed them. What are they? Yep. Force of gravity and, but they cancel each other out, right? That's kind of why I left them off. Really, we should draw them in because they're there. But in the end, they cancel out. Cody, question? Nope. All right, next step. Net force is equal to the sum of the forces. That's going to be FF plus FB plus FA. Now, since we're looking for the acceleration, we're going to set F net equal to M times A. We don't always do that, just when we're looking for acceleration. M times A is equal to FF plus FB plus FA. And we're going to plug in some numbers here. 450 times the acceleration equals a negative 430 plus 1,200 plus 1,220. And then we're going to do the math and find what A is. Works out to be 4.4. Once you get to this part, right, it's physics. Okay, getting to this part is physics, but also reading and seeing what's important. Just because you're given a number, this is the trap we like to fall into. We don't like to fall into it, but we do fall into it. Just because you're given a number doesn't mean we're going to use that number. We usually do, but not always. Okay, look at it on a case-by-case basis and figure out, does this number really matter? Okay, this one doesn't, any more than the color that I'm allowed to paint my sled matters. Here's a practice question for us in preparation for Monday's quiz. We got a situation where we got a coefficient of static and kinetic friction. We got a mass of 100 kilograms. We're applying 4 different forces. In each of these 4 cases, I want to see what the force of friction is. Okay, what is the force of friction? And what kind of friction is it? Static or kinetic friction? Let's have a look at the question now. Hey, in order to do this, we have to know in each case whether it moves or not. Whether it moves. So does it move when I apply a force of 400 newtons, 600 newtons, 800 newtons, 1,000 newtons? How do we find out whether it moves or not in each of these cases, Ollie? Yeah, you got to use the force, static maximum. So we're going to calculate that maximum force of static friction. It's not the answer to any of these questions, but it's a necessary step in answering all of these questions. We're going to say FSF max is equal to mu times the normal force. The coefficient of static friction times the normal force. So 0.75 times 100 kilograms times 9.81. And I think when you do this, it's like 735 or something like that. 735.75. Thank you. 735.75 newtons. Now, again, that's not the answer to any of these four questions, but it is enough to tell us in all of the four questions whether it moves or not. Does it move in question A when I push on it with 400 newtons? No. Does it move in question B? No. I've got to exceed that maximum force in order to get it moving. I haven't done that in question A or B. What about C? Yeah, it moves. I exceeded the force of maximum force of static friction. What about D? 1,000 newtons? Yeah, I've exceeded it, right? If I push with more than 735, then it's going to be kinetic friction. All right. Let's go back to A and B. Okay, A and B are kind of different than C and D, right? Because A and B are the problems where it's static friction, it doesn't move. C and D are the problems where it's kinetic friction because it does move. What's the force of static friction in question A? Matt? 400 newtons, right? Static friction is that force that pushes as hard as it needs to push up to, but not exceeding the maximum force of static friction. So listen, it can push with 400 easily. If I push with 400, it pushes with 400. Think of it this way. If it doesn't move, it's in a state of, two words, SE. Somebody said it? Static equilibrium. If it doesn't move, it's in a state of static equilibrium. If it's in static equilibrium, the forces must be balanced. If I push with 400, it must be pushing back with 400, right? What if I push with 600? Well, it's still not moving, so it's still in a state of static equilibrium. Forces must balance. If I push with 600, it pushes back with 600 because they've got a balance. Static friction force in that case is 600. Now it moves. Now it moves in question C. Now it's not static friction anymore. Kinetic friction. How do I find the force of kinetic friction? Is it 800? No. How do I do it? Which formula? Yep. Okay, that's good. So the coefficient of kinetic friction is 0.5 times 100 times 9.81. That gives me, I think when we do that, I think it was 491, wasn't it? 490.5, rounded to 3 digits, 491. Actually, it should be rounded to 2 digits, right? 4.9 times 10 to the 2. All right, so what's my kinetic friction going to be in C? Kobe? 4.9 times 10 to the 2. Right? I've exceeded the maximum possible force of static friction. It moves. But there's going to be a force of friction still resisting the motion, but now it's kinetic friction, which is a little bit lower than the max force of static friction. What's the force of kinetic friction going to be in D? Right? 4.9 times 10 to the 2. Remember that static friction force is kind of the pain in the butt force. It's the one that pushes, that keeps pushing. Right? I push with a certain force, it responds to that. Right? I push a little bit harder, it pushes back a little bit harder. I push a little bit harder still, it pushes back a little bit harder until the maximum force. Kinetic friction is kind of that laid back force, that consistent force. Hey, you know what? I'm happy being the force that I am. Okay, 4.9 times 10 to the 2. Doesn't matter how hard you push. I'm just going to push back with the same force as I always push back. Okay, 4.9 times 10 to the 2 newtons. What if I created a question E that said my applied force was 17,164,112.64 newtons? What would be my force of kinetic friction? 4.9 times 10 to the 2 newtons. Remember, it's that consistent force. It just does the same thing all the time. You can count on it to be the same all the time. You guys feel okay about that? How many people got that? Okay, good. If you can get that, you're going to nail Monday's quiz for sure. Okay, if you didn't get it, make sure that you understand it and talk to me. You guys have time scheduled help on Monday to have a chat with me about this, okay? You know what you're going to see on Monday, so make sure that you can do something about it. All right, the new stuff that we did yesterday was on Newton's third law, but I'm just going to refresh your memory on his other 2 laws first. Newton's first law and Newton's second law. Remember, Newton's first law is the law of inertia. It's kind of, think of it as the law of balanced forces. Newton's second law, sometimes you could think of it as the law of unbalanced forces. Okay, we're in equilibrium in Newton's first law. First part of Newton's first law relates to static equilibrium. If an object is at rest, it will, not a force, but an unbalanced force. Good. An object at rest is going to stay at rest until an unbalanced force acts on it. An object in motion is going to want to stay in motion at a constant speed in a straight line until an unbalanced force is acting on it. So in other words, an object keeps doing what it's doing. The law of inertia. It doesn't want to change its motion. The law of, you could say, the law of equilibrium. Right? The law of balanced forces. All kinds of things you could call it. Everything's balanced. It keeps doing what it's doing. If it's at rest, it stays at rest. If it's moving, it stays moving. Newton's second law, on the other hand, we could think of it as, it's not really called this, but we could think of it as the law of unbalanced forces. You've got an unbalanced force here, and that causes acceleration. The acceleration of the object is related to that unbalanced force, but it's also related to something else. What is it? I shouldn't say it's related to something else. It's inversely related to something else. It is? Good, the mass. If the force goes up, the acceleration goes up. As the mass goes up, the acceleration goes down. Forces are balanced, forces are unbalanced. The third law, this is what we talked about yesterday. We're talking about unbalanced forces with the third law, but we're talking about unbalanced forces on 2 different objects. Newton's third law, as you learned it back in grade 6 or grade 7, said for every action there's an equal and opposite reaction. But we now like to state it slightly differently. No more correct, but in a way that helps us to understand it more. If object A applies a force on B, B applies an equal and opposite force on A. The reason we like to say it that way is because it reminds us that there's 2 separate objects acting. Okay, we don't do that. We don't make that mistake that we made yesterday and say, oh, wait, the action-reaction forces balance each other. They don't, because the action-reaction forces, although they are equal and opposite, are acting on 2 different objects, causing an acceleration for both of those objects. An acceleration that would be equal to F over M for each of those objects, right? Yesterday we gave you a situation where your fist goes through some glass. Not that you'd want to really do this. Do you find that Newton's third law was still valid in this situation? Always is. It always is. Okay, if you get any question, even if it's out of context, even if it's a question that you haven't seen before in class, if you get a question that asks you basically, is Newton's third law valid? The answer is yes. It doesn't matter what the context is. It's always valid. If I punch the glass and the glass breaks, hey, maybe 50 newtons was required to break the glass. My fist applied a force on the glass of 50 newtons. How hard did the glass push back in my hand? 50 newtons. That is, while the glass wasn't broken, right? As it was breaking, it applied a force back of 50 newtons. Glass broke, my hand didn't. How come? Because the glass is weaker than my hand. Could go the other way though, right? You go punch something like a brick wall, Maybe your hand breaks. I apply a force of 50 newtons on the wall. Wall applies a force of 50 newtons back. The wall survives, my hand doesn't, because the wall's stronger than my hand. What if I throw that rock through the window? Not that you're ever going to do that either, because that would be vandalism, and that would be bad. But let's say we did for a second throw a rock through a piece of glass. Rock applies a force on the glass, breaks the glass. The glass applies an equal and opposite force on the rock, but doesn't break the rock, doesn't even stop the rock. What does it do to the rock? Slows it down. It could deform it, or it could slow it down. In all likelihood, it's going to just slow it down, right? So one force causes breakage, the equal and opposite force causes a deceleration. Yep.
So say like if it's like more, an example, like a rock in it.
Yep. Yep.
No matter how fast you go, even if it's a bullet, it will always like slower like speed when it's
yep.
make contact.
Yeah, I'm glad you brought up the bullet. Actually, that's a great example, a great case of. Let's say a bullet went through a piece of glass. Usually, a lot of times the glass doesn't actually shatter when a bullet goes through it, right? It's going so fast it goes straight through, punctures it, but doesn't shatter the glass. Sometimes it would, but not always. The bullet clearly applies a force, a pretty big force on the glass, right? Because it goes through the glass, right? Does the glass apply an equal and opposite force on the bullet? Yes. Doesn't matter how fast the bullet's moving. Now, does it slow down the bullet? Yes. It doesn't necessarily slow down the bullet dramatically because the bullet was moving so fast. But if you could measure the speed of the bullet before it hit the glass and after, yeah, it's going to be slower. How much? Depends. Depends on how much force was applied, right? Yep. Yep. Okay, good question. I like these questions. I mean, keep asking them, right? Because that's what really gets us an understanding of things, is asking those questions, right? So your question, and I'll just clarify it for everybody and just make sure I got the right, make sure I've got it summarized properly here. You hit a piece of glass with a hammer, or it's not a piece of glass, but a piece of ice with a hammer, and you don't break the ice, but you crack the ice. Okay, so you applied, let's say, a force of 100 newtons on the ice. It cracked it, but didn't break it. And then you hit that piece of ice again, and it shatters because it's weaker now, right? Make sense? That's what I've summarized it properly? Okay, so what's happening there? Well, you hit the piece of ice with a force of 100 newtons. That's enough to crack it. The ice applied a force of 100 newtons back on your hammer, right? Now I go down with the same motion with my arm with the hammer to hit this piece of ice, and the ice breaks. It's weaker now. So it requires maybe only 75 newtons to break it now. How hard do I end up pushing on the ice? 75 newtons. I hit the ice with 75 newtons. It pushes back with 75 newtons. Okay, in the end, no matter how hard I hit the ice, no matter how hard I swing, the ice broke at 75. Make sense? And it's going to push back on my hammer at 75. That's why the first time I swung my hammer, I felt a lot more resistance when I hit the ice with the hammer. The second time I felt less resistance when I hit it with the hammer because the ice just wasn't as strong. It broke before that much force could be applied. Good? All right, I want to do one little math problem, and then I'll leave you with one little math problem for the weekend. Besides your quiz, that's going to be it. Mr. Dickie's mass is 70 kilograms. Let's pick somebody here. Who are we going to pick here? Somebody that doesn't have a mass of 70 kilograms. Kobe, what's your mass? Do you know what it is? What is it in pounds? 195, so you're probably 85. We'll say you're 85 kilograms. Kobe's mass is 85 kilograms. Kobe pushes Mr. Dickie, causing him to accelerate at 2.5 meters per second squared. What's Kobe's acceleration? All right, so how do I tackle this question? How do I tackle this? Mr. Dickie's mass is 70 kilograms. Kobe's is 85. I accelerate at 2.5. What's Kobe's acceleration? Hey, give me an estimate here. Do you think Kobe's acceleration is going to be more or less than my acceleration? Equal acceleration? Okay, you say it's going to be less. Anybody say more?
So acceleration like
Yeah.
running or
No. So Kobe and I are pushing each other. I accelerate at 2.5. Kobe weighs more. Is he going to accelerate more or less or the same as I do?
accelerate slower.
Why is he going to accelerate slower? Okay, so let's see now. Okay, somebody says it's going to be the same. Somebody says it's going to be less. Let's see. Let's say that the force of object 1 on object 2 is equal and opposite to the force of object 2 on object 1. Equal in magnitude, opposite in direction. We're going to say m2a2, so the mass times the acceleration of object 2 is equal to negative m1a1. The mass times the acceleration of object 1. Let's sub in our values here. Let's call m2 Kobe. 85 times Kobe's acceleration equals negative 70 times my acceleration. Let's do the math here. Let's say 70 times 2.5 divided by negative 70 times 2.5 divided by 85 gives me an acceleration of 2.1, negative 2.1 meters per second squared. Hey, why is it negative? Yeah, it's opposite direction, but it's not equal. Didn't we say Newton's third law always was valid? How come it's not equal? How come it's not equal, Connor? Yeah, the forces are equal. Object A applies a force on object B. Object B applies an equal and opposite force on object A. It doesn't mean the acceleration is going to be equal, right? The same force accelerates a heavy object less. You push on your smart car with a certain force. You push on a semi-truck with the same force. Which one accelerates more? The smart car, obviously, right? Because it has less mass. I'd like you to do this question for homework, please.